So now that we have our feet wet from really kind of getting an idea behind what a change of variables is in general and how we've been using it kind of subconsciously and this thing called the Jacobian, now I'm going to go over an example that kind of shows, this trial and error method of what exactly were people doing when we were discovering change of variables, and how exactly does this whole thing work. And so what we're going to do is we're going to start off with a pretty simple region in U and V land, right? And so this is the point 1, 0. This is going to be the point 0, 1. And the idea is that we have a dream of doing some double integral, okay, dA, or, du, dv, dv, du, but dA. And that's our dream, right? Okay, and why is that our dream? Because I know that the bounds for u that I've picked go from 0 to 1. The bounds that I picked for v go from 0 to 1. And I'm just like, wow, this is a really nice integral to do. I wonder what shape I could use from x and y land, what shape I could be integrating over there that would come back via some transformation and give us this exact double integral. And so, as I mentioned before, you're going to be given the transformation yourself. And so for this particular example, I'm going to give us the transformation x is equal to u squared minus v squared, and y is equal to 2uv. Okay, this example is also in the textbook, as are most of the ones I'll be going over from here on out, just because it's nice for you all as students to have a secondary source to go through and read a little more in depth in case something I say here doesn't make complete sense. So remember, right now, our job is not to do anything else but to figure out, if I put this shape through my transformation, what shape is it going to look like over in x and y land, okay? If this was r cosine theta and r sine theta, we know it would give us a circle, and that's really nice because we know how to integrate circles. Hooray. So in order to do this, there's a little bit of theory behind why what I'm about to say works the way that it does. But the idea is that there is a theory that says, there's a theorem, and I'm not going to write it down, I'm going to say it verbally, but pay close attention. The idea is that if I take this box, okay, and I split it up into these 4 kind of bounding lines, okay, that are basically containing my region S. Okay, remember this is the region S in here. And so we might call this first line here S1. We might call this second one here S2. We might call the third one here S3. We might call the fourth one here S4. It basically says that if you put each of those boundaries through this transformation, that they will connect over here in whatever way, right? And the idea is that they will create the region of integration over here. So that basically, instead of doing this for every single point on the inside of S, we only need to figure out what happens to basically the outside edges of the shape, the boundary of this shape. Okay, so what on earth does this mean? Okay, let me try and talk about this. So for instance, let's see where S1 goes under this transformation. Okay, under this transformation. And so here's the way that we can go about doing this, okay? So the first thing that we need to do is we need to describe this curve right here. It's not a curve, it's a line, but a curve is just the general term for anything. But we want to describe this part of the square. Well, that part of the square right there, S1 can be defined by it's just a line. It's v equals 0. And how long does v equal 0? Well, v equals 0 so long as u goes from 0 to 1. Okay, so that is specifically this little segment right here at the bottom. Okay, that's my S1. All right. And so the question is, what happens to this little line segment if I put it through this transformation? So using the transformation, remember in the transformation we have x is equal to u squared minus v squared and y is equal to 2uv. Well, this line, right, what's going to happen to it? Well, if I plug in v equals 0, this line into this transformation, what do I get? I get that x is equal to u squared, and I get that y is equal to 0. Okay, great. So what else do we know? Well, we know that u goes from 0 to 1. Okay, so if I plug in 0 in for x, I'm going to get 0. And what's the largest value of x that I'm going to get? Well, if I plug in 1 in for u, I'm going to get 1. And so this basically tells me that my x values are going to range from 0 to 1, while my y value just stays equal to 0 because there's nothing to do with it. So what is this? Well, this is the line y equals 0. From x goes from 0 to 1 over in xy land. So it's this chunk right here. Okay, that is what happens to S1. And you're like, oh, it's the same thing? Yeah, this one turns out to be the same thing. Well, that's great. Okay, fabulous. Now let's do S2. Okay, so I'm actually just going to erase this because I want you to be able to see what we're doing all at once. So let's go ahead and try S2, right? What is going to happen to this right line? Okay, so S2 can be described by what? Well, it looks like, visually, it is a straight line given by u is equal to 1, and it's that straight line for the values of v that go from 0 to 1, okay? From here, right, v equals 0, v equals 1, and u is equal to 1 the entire time. Great. So inside that transformation, what happens? Well, if I put u equals 1 in our transformation, I get x is equal to 1 minus v squared. And I'm going to get y is equal to 2v. And again, I haven't done anything with this information yet. But one thing I want to point out is that this is not something that I can graph over here. At least not yet, right? We had a problem on the review assignment where I said, if you have parameterized equations, can you get rid of the parameter and turn them into just x and y? And so here we're going to actually do that same thing. And what we're going to do is I'm going to actually solve this second one. I'm going to solve this second one for v, and I'm going to plug that into the first one because I want this equation to be in terms of x's and y's. And that very quickly gives us that x is equal to 1 minus y over 2 quantity squared, which is equal to 1 minus y squared over 4. Okay, so this is the shape that we get. Now, what is this? Right? Well, this is an upside down parabola. Okay, it's an upside down parabola. Now let's kind of examine really quick. So how do I know what this looks like? Because an upside down parabola that's shifted up by 1 unit, would look something like this, right? Okay, this might be what it looks like. So we need to actually use the thing that we haven't used yet, which is this bit of information right here. The fact that v goes from 0 to 1, which means that y goes from what? That immediately gives us that y is going to be trapped from 0 to 2. So that means that this parabola is not going to go down, right? It's not just going to keep shooting down like this indefinitely. We have a boundary for our y values, okay? We have this. And actually, I just realized this is not a normal parabola. This is a sideways parabola. Okay, so x equals 1 minus y squared over 4 actually starts here because when y is 0, we get x is equal to 1. And I know for a fact that it's going to go this way. How do I know? Well, number one, it's x equals 1 minus y squared over 4. And number two, I know that my largest y value here is 2. How do I know that? Because we just figured it out using our cap on the v-bound. So maybe I'm not going to put this little head. So this is basically, that part of the graph. Okay, this right here is our S2. That's what our transformed S2 becomes in x and y land. It is this parabola, x equals 1 minus y squared over 4 for the values of y that go from 0 to 2. Okay, now let's keep on going now that we're kind of getting the hang of this. So let's do some more. Okay, so now let's move on to S3. Okay, S3. So S3 can be defined by the straight line v is equal to 1, and u goes from, okay, so now we actually have to be careful because I drew those arrows for a reason. U goes from 0 to 1, but it's doing so in a particular direction. Okay, it's actually going from 1 to 0. This ends up being kind of important that we provide some direction to this, and I haven't said why it is yet, and for now I'm not going to. It's just going to be something that we're going to keep in our mind, that I claim that we want to kind of keep going in a particular order. The reason it has to do with, like, if you're building pieces, you want to go from one to the other, to the other, to the other, like that. And you don't want to accidentally, be connecting lines and go from one to the other, to this, to that, like that, and create an incomplete piece. Okay, we want to go tail to tail to tail to tail. Okay, so S3 is the line v equals 1 for 0 less than or equal to u less than or equal to 1. Great. So what happens to our transformation? We get x is equal to u squared minus 1. Y is equal to 2u. We do the same thing we did before, and we're going to get x is equal to y squared over 4 minus 1 by canceling out some the parameter u. We're going to pay very close attention to the fact that u goes from 0 to 1, which again is going to make our y value go from 0 to 2. But remember that even though I keep saying u goes from 0 to 1, what we're actually doing is u is going from 1 to 0, so y is going from up here at 2 down to 0. And then we have to use our brains to recognize that this is a shifted parabola that starts at minus 1, 0, and would kind of have that shape, okay? But we're going down this way. So maybe I'll put like some little arrows here to kind of indicate our direction of travel here, okay? So that little green piece is this x equals y squared over 4 minus 1 as y goes from 2 to 0. And so we're going to cap things off by doing the pink piece, and that's going to kind of be, well, this won't be the end. I'll do one more short thing with this video. So S4 is going to be the line u equals 0, where v goes from 1 to 0. I'm going to write it like this, v less than or equal to 1. But v is going up from 1 down to 0. So what happens to our transformation? We get x is equal to negative v squared, and y is equal to 0. What happens when I let v go from 1 to 0? What values am I going to get? Well, I'm going to get x goes from negative 1 to 0 as well, which we get by just plugging in these values for v, kind of seeing what's going on. And so that tells us, coupled with the fact that this function is clearly the line y equals 0 as x goes from negative 1 to 0, it's going to tell us that our final answer here is basically the line y equals 0 going in this direction as x goes from -1 to 0, and this is line y equals 0. Okay, great. And notice that the first one we did was also y equals 0. And you'll notice this creates, right, this region of integration over here. Now what is this? I don't know. It kind of looks like an airplane hangar or something like that. But the point is that if, right, so the big purpose of doing this whole shebang, okay, actually, let's erase this and let's just sink in the whole purpose of everything that we just did here, okay? So what you might see in a problem is, for example, use the change of variable, okay? Use the change of variable. X is equal to u squared minus v squared, and y is equal to 2uv, right? Use this to evaluate the double integral over some region R of, let's say, y dA, where R is the region bounded, right? Is the region bounded by the x-axis and the parabolas. Which parabolas do you think? X equals 1 minus y squared over 4, and x is equal to y squared over 4 minus 1. And you're like, okay, I don't see it. Well, the whole point is this question is asking us to integrate over this region R right here. That's what we're being asked to do. Now, if we had to do this using Cartesian, we'd have to probably split this thing up, come up with some pretty funky bounds, keep it an x and y. But lucky for us, we know already that the double integral over this region of y dA, we already know that using the transformation, using this transformation, this change of variables, becomes, right, it's mapped to the perfect little square where u goes from 0 to 1, where v goes from 0 to 1. We get a du, dv, or dv, du, doesn't matter the order here because it's a perfect square. And if we use the change of variable, that y is equal to 2uv now, right? This y over here is now this. We're almost done, right? Like this integral looks way better to do. What is the only thing that we're missing? Well, it's the thing that I mentioned in the last video, which is basically the price we pay, the distortion factor. We're missing the Jacobian with respect to u and v. But lucky for us, that's not really going to be that hard for us to calculate based on our information before. Remember that the Jacobian, all we really need to do is to figure out some partial derivatives and take a determinant, right? So if we remember, we're going to have this determinant, and what goes inside of it? Well, we're going to take the partials of x with respect to u, partial of y with respect to u, and then we do the partial of x with respect to v, we take the partial of y with respect to v. And so for us, in this problem, what do we get? We get, we're going to get the magnitude of, well, what's dx du? Dx du is 2u. Dx dv is a negative 2v. dy du is a 2v. And a dy dv is a 2u. And so what do we get here? We get 4u squared plus 4v squared. And, well, what do we do with this? Well, that is our Jacobian, right? This right here is our Jacobian. And it may not look very nice, but that is going to go right inside there. So if we wanted to evaluate this double integral, 0 to 1, 0 to 1, 2uv times 4u squared plus 4v squared du dv, you might look at this and say, wow, this looks terrible, oh my gosh, but this is just a polynomial, right? The Jacobian here is just a polynomial times another polynomial. The bounds are super, super nice. They're 0 to 1. What more could you ask for in life, right? So, and you're like, well, Dylan, what, couldn't we just have looked at this area over here and just been like, all right, this is our region of integration. Why don't we just split this into like 2 regions, let x go from 0 to 1, let y go from 0 to whatever this upper bound is, let y go from that, right? Could we do it? Yes, you're absolutely right. We could do it. But if you just discovered that this transformation right here takes every single Hershey's Kiss shape that has 2 parabolas as like the bounds and a straight line for the bottom, and you just discovered that if you use this parameterization, right, this change of variables, then you always get to set up a double integral with bounds from 0 to 1, and you always get to set up the Jacobian, which is 4u squared plus 4v squared, and all you have to do is to change your variables from y into 2uv or from x into u squared minus v. If that's all you have to do and you can do it every single time, forget this one. Forget doing this 1,000 bazillion times. Just follow the pattern. We could use this transformation as many times as we want. Okay. Now that's not something that I'm trying to really focus on in this little section. The whole point of this again is if we start with a region, a nice region in terms of u and v, we're given a transformation, right? What does it look like in x and y? That's pretty much the goal of what we're doing, okay? So we're going to pause here. I think I might do one more video, maybe with one more example after this, but for now, I think this is a good place to stop, let you all kind of catch your breath, and we'll keep going in the next one.